This is lesson 9 of the Quantum Mechanics, a mini lecture series, Photoelectric Effect Part 2. So in the previous video, I talked about the photoelectric effect, okay, which is basically the phenomenon whereby electrons are emitted from a metal surface when light of a very specific frequency is applied. And I should mention this, light of a certain frequency is needed, okay? A very particular light of a particular frequency must be used to get electrons coming out of a metal surface. Okay, electrons. Okay, that minus indicates the charge of the electron. Remember, frequency is how many waves pass through a certain point per second. Okay, high frequency means short wavelength, a lot of peaks. Low frequency means not many peaks, long wavelength. And I should also mention metals. So metals, the metal atoms making up a metal, they share their electrons. Okay, this is called metallic bonding. And the electrons in a metal, they're delocalized. Delocalized means they're free to flow and they're shared amongst all the metal atoms. And when you get delocalized free electrons, okay, electrons which aren't bound to the atom, you get current flow. And that's why metals are so good at being electrical conductors and thermal conductors. And electrons leaving the emitter from before, so remember there was an emitter from the Lenard setup, they've got a certain kinetic energy. Okay, kinetic energy is moving energy. Okay, obviously because they're in motion. And they continuously lose this energy as they travel against the retarding voltage. So think of the retarding voltage as like hands sticking out. Okay, they're pushing the electrons away from the emitter. Remember there was a plate here connected to a battery. And to make it past the retarding voltage, the electrons must have initially had an energy greater than Q V sub naught. Now Q is just charge of the electron. In physics, Q stands for charge, it's a number. V sub naught, that's the retarding voltage. Okay, they have to have an energy greater than this. Whenever an electron is in a moving electron, when there's a voltage applied to, let's say, a plate, it'll feel a force, okay? And that force is dependent on the voltage, retarding voltage in this case, and the charge itself, okay? The electron, what it feels is the result of its charge and the voltage. Now, classically, according to classical physics, the emitted electrons must get their kinetic energy from the light beam, okay? Which is pretty much logical, right? Conservation of energy. The law of conservation of energy is one of the most fundamental, basic laws of the universe. It states that energy can't be created or destroyed. So energy from the light goes to the energy of the electrons. And according to classical physics, the picture was this. Light would strike the metal in terms of waves, okay? And more intense light, okay, brighter light, indicates more energy for the electrons. But this wasn't what Lenard found in 1902. That's wrong. Okay, rather, the electron energies were entirely independent of the light intensity. Okay, light intensity, there was no correlation between light intensity and electron energy. And also further experiments show that there was another unexplained effect. There was a certain threshold frequency below which no photoelectrons were ejected, regardless of how intense the beam was. Okay, so in other words, there needed to be a certain frequency of light required to get electrons ejected from the metal. This was very puzzling, and this is where Albert Einstein comes in. And I'll talk about this in the next video.